Okay, so without further wait time, welcome everyone to our colloquium. It's a great honor to have Philip Kim make the long travel from Harvard down here. Thank you very much. I believe everyone in the audience knows Philip Kim by some means, if at the very least from your solid-state physics course, where it's hard to get around him. And if not, please make sure to look him up later. You'll have an idea from the talk today. Philip started off working with Charles Lieber as a PhD student, working on carbon nanotubes, which is a subject that's also close to my heart. Then worked with Paul McEwen as a postdoc, and then started as an assistant professor at Columbia University, where he stayed from 2002 to 14, when Harvard snatched him to come over here. And I think that's to great success for the scientific community for sure. I will say that, well, graphene is sort of tightly bound to his name. So there have been really foundational works on 2D materials that are due to Philip. Long list of accolades. I'll only say that he's a member of several academies, like American Academy of Arts and Sciences, Korean Academy of Science and Technology, APS Fellow, and so on. He got noticeably also the APS Oliver Buckley Award in condensed matter physics, which is the highest, if you want, award for condensed matter physics that exists. It's a timely visit. The UN proclaimed this year as the International Year for Quantum Science and Technology. And even though he didn't intend it, I will just read one description that they have saying, anyone, anywhere can participate in this international year, helping others to learn more about quantum at this centennial occasion. And so we're looking forward to the talk that, if you want, you can read as searching for anyone in quantum materials. So if you don't know what an Anyon is, you'll learn about it from Philip. Without further ado, stage is yours.
Thank you. Yeah, thank you. Yeah, thank you. I realized that Matthias actually made the really exciting joke, and I didn't know until he pointed out it could be any on, but anyone is make the better sense. I think that was kind of nice, the comments he made. Thank you very much for inviting me again to the Brown. I think this is my probably fourth or fifth visit ever, and the last one was during the pandemic, and I just couldn't come, and this is after pandemic. It's kind of first visit, such a long distance. Sometimes it makes it difficult to visit. It was great to be here and just kind of meeting old friends and new friends and together. So I will tell you about this searching for Anyon in quantum materials, and I will of course kind of explain what is Anyon that I meant, and also how we can find out and see something interesting into some quantum material platform. So that's what I'm going to tell you. So let me starting from the Anyon rather than anyone. So idea comes from basically the fundamental kind of quantum physics idea. So if you have the two indistinguishable particles in quantum mechanics, I think indistinguishable particle means that even if we just kind of name this particle, that if you should change the name, that we don't know whether it was changed or unchanged, basically it's the same thing. Exactly same particle, basically there is no way that we can distinguish between them, right? Because of this, the completely indistinguishableness in the quantum physics tells you that this can be fundamental symmetry that quantum physics impose. Therefore, there is a consequence for that. And consequence is kind of rather striking. What quantum mechanics tells us is if it is an indistinguishable particle, they can fall into the two different categories, and that's it. And that two different categories, once you just change the name of the particle, index of the particle, so wave functions stay the same sign versus different sign. There are only two choices possible. And when wave function changes the sign, that we call the fermions. And if wave function doesn't change the sign, it's boson. And turns out that once you just include the spin degree of freedom, that all the bosons is related with the integer number of the spins, and while the fermion is associated with half integer number of the spin, half integer spin. While this is kind of really exciting idea, the one thing that we didn't learn or we didn't teach typically is in the 3D. This is true for the 3 dimension and higher, but once you get into 2D, there's another possibility. I think that's kind of interesting, the scheme. What is the difference in the 2D is that when you just think about this changing the name of the particle, this is related with, in some sense, changing the position of the particle. One way that I can change the position of particle is just kind of put one particle there and put the other particle on the other side, right? So it's kind of half of this the rotation, or half rotation is kind of get involved in here. And because of this one, that you can see that that's why that is related with spin degree of freedom, which is a related rotation degree of freedom of this operation. In the 2D, those kind of the changing the positions, or what we often call the braiding operation, is often that topologically unique. Part of the reason is that when you just kind of braiding of these things, unless that you just kind of really make the cut, the winding numbers associated braiding is a really well-defined the integer quantity, or the topological invariant quantity in the 2 dimension, and make the kind of other possibilities possible after you just kind of do this exchange of braiding operation. And one kind of easy consequence out of the mathematical point of view is in the 2D, therefore, that once you just change this particle indices, in fact, the wave functions can carries this the phases, and this phase in principle can be okay. So this one doesn't work too well. So this phase can be in principle any number, and later this phase can be certain kind of fractional numbers in typical ground state. Important part is this phase in principle can be anything, and that's where that often that the first people just kind of coin this or come up with the idea, including the Frank Wilczek, names those kind of the quasiparticle that if it indeed exists in the 2D and satisfying this type of the exchange statistics called the Anyon. And this Anyon becomes kind of even more exciting if there is a ground state happen to be the degenerate states, which means that after braiding there is even the possibility that one can map the one of the wave function to another one by just kind of unitary transformations between them, right? And this unitary transformation, allowing these unitary transformations can map into the after braiding, the particle can change its nature to the another particle, making this one is even more different type of the statistics, getting into so-called this non-abelian Anyon. This doesn't seem to work too well, so let me switch my clicker. Sorry. Right. And up to here, this is kind of completely mathematical, the idea that one can coin through. But of course, nowadays, this is a non-abelian Anyon. The anyons, especially this non-abelian Anyon, becomes quite important topic because once they have this non-abelian Anyons, that there is a way that by just simply braiding this particle, so you exchange the position of this particular anyonic particle, there is a way that you can encode this information non-locally in the space, which actually topologically protected because of this braiding nature of the braiding. And idea is using that one can build up the qubits that topologically protected, such that which allows you to have the fault-tolerant kind of quantum computation. So in some sense, in the 80s, when this concept of the Anyon comes around, and until then now, I think there has been some now the renewing this interest to find out the Anyons, especially non-abelian Anyons, and demonstrating their manipulations, and just try to use this as some the fault-tolerant quantum computing is one of the really important topics in condensed matter physics in general in past probably 2 decades or so. Where we can find out this the Anyons then. There has been some ideas around that how to find out the Anyons, and then demonstrating this the manipulation Anyon and the existence of Anyons. And the first system historically that the existence of the Anyons and some search of the Anyon happened was a quantum Hall system. When you apply the extremely strong magnetic field in the 2-dimensional electrons in the low enough temperature, there is a strong correlation appears in electronic system. So electron in the 2D start to demonstrate this first integer quantum Hall, but then once you get into extreme quantum condition, electron also shows fractional quantum Hall states. many of the excitation of this fractional quantum state is believed to the Anyon, and in particular, if you go to the even denominator states, the fractional quantum state, there the quasiparticle excitation is found to be believed to be non-abelian Anyon. And there has been some of the experimental the efforts as well as the theoretical proposals to use this even denominator states and their quasiparticle for quantum information processing. The other class of the material is so-called the topological superconducting class, and where that system can be realized by combining superconductor with the sum of the topological system. It can be topological insulator, it can be 1D wire with a very strong spin-orbit coupling, or it can be just kind of ferromagnetic wires on the top of the superconductor, or atomic chains of this type of things. And many of the system is basically combining with the superconductor with the sum of the topological material, and just realize so-called the topological superconductivity, where the defects or the vortices in there is often contains this localized localized non-abelian Anyon states in there, and using that as just a vehicle to realize the physics I'm just kind of telling you. Again, this has been about 20 years of efforts that communities put quite efforts. So there is all sort of the stories out there that discovery and not discoveries or new discovery and things. All of these stories at this point is a kind of developing story, I would say. There has been quite a progress in communities, and then it's kind of interesting to just look at this the progress in some sense. So I just try to give you that, if time allows, 2 examples that relate with each of this topic going in my group, and give you just some of the status where the communities are, and the using this the experiments going on in my group as a vehicle. So that's kind of my goal today. Okay, so the first part I'm going to tell you is Anyon in the fractional quantum states, and this is related with the building up the interferometry of the Anyons, and demonstrate how we can just prove that existence and how we can manipulate them, and you will see there's some flavor that what type of the directions we are moving on to really go to demonstrate the non-abelian Anyon. So this part that the few people and most important people is these 2 people, Tom and James, that who did most of the experiment I'm going to tell you today in collaboration with Ami Yacobi's group, and then the theory groups, the theorists they helped, both Harper and Harvard, and also Dima Feldman here, also help us a lot to just understand that what we are measuring in our devices. And then the boron nitride crystal, which actually plays a very important role to make the high quality device, comes from Japan. Okay, I already told you that the fractional quantum state is one of this nice platform one can realize this anyonic physics. And the reason is, once you get into extreme quantum limits, then you can see that a lot of the interesting the quantum the whole state appears, and many of the quantum state appears is fractional numbers. And although this looks very complicated, there's a neat way that you can explain this all the fraction, most of the fraction we are seeing here, and that is the so-called the composite fermion pictures. And that is in some sense that you just have the electron, that the electrons start to grab this quantized the magnetic field, kind of come together and form this new composite fermions. And then once that you form this composite fermion, and composite fermions of the quantum state can explain this all this the many of these integers there, and that has been kind of well-established theories that understanding fractional quantum states in terms of composite fermion. It turns out this composite fermion has the excitations, anyonic excitation. In particular, that also anyonic excitation has a fractionalized charges. So one thing that you can quickly see that is many of the excitation of this fractional quantum state is related with this the fractional excitation of this quasiparticle, the anyonic quasiparticle. And this fractional charged anyonic quasiparticle contains also the statistics, braiding statistics of anyons, and which is in particular characterized by this the braiding angle theta that often I just mentioned, which is if it is a fermions, it is the theta becomes pi, and if it's boson, it becomes 0 or 2 pi. But if it is Anyon, this is somewhere in between. In particular, in this type of the quasiparticle, often the 1/3 state, for example, is coming with pi/3 of 60 degrees of the this braiding angle is there. And if you just choose different state, you have the different fractionalized charges and different braiding angle. And one important part of the this fractional quantum Hall state is an even denominator state. I briefly mentioned that even denominator state is in fact considered as a non-abelian state. So here that even denominator state can be understood in some sense. You have the two composite fermions and just make the pair, and then as the pair of the composite fermions that they can be condensed down as if the BCFs like the state, and those kind of condensated state can explain that this even denominator quantum Hall states. And the belief is that indeed the quasiparticle excitation of those condensation state is related with the non-abelian anyons with the fractionalized charges as well. So that's kind of some of the directions to kind of move on. So how one can prove that existence of anyons, either abelian and non-abelian cases. And one way you can just kind of realize that proving this the existence of anyon is using the interference techniques. And that comes from that using the Aron-Bohm effect. When Aron-Bohm that wrote this paper in the 1959, the idea was rather simple, but already kind of very powerful in the following way. Let's say that if you have any quantum particle, it can be fermion bosons or anyons, doesn't matter, any quantum particle, can be explained in terms of wave functions. If you have the beam splitters of the wave functions of the quantum particle split into the kind of two different paths and let them pass through and just recombine them. And then in this path that you just thread this magnetic field, you can quickly write down this the quantum particle will just kind of the wave function will gain. This phase is dictated by the Aron-Bohm phase, and those Aron-Bohm phase contains the information about the charge that carried by this the wave function, right? Therefore, in some sense, just looking at this the interference pattern, you will immediately get the sense that, and just observing Aron-Bohm phase, you get whether this charge that I'm just kind of sending into this interferometer is fractionalized, right? But also, because of this technique, is very sensitive to this phase of this wave function. If I have the particles inside of here that and cleverly created those kind of interference path, there's a way that you can also detect this the braiding phase of the particle. Of course, electron boson is probably insensitive, but if it goes to Anyon, there's a way that we can make those kind of phases sensitive to the braiding angle, which I'm going to discuss in a moment as well, right? And of course, this idea is a kind of fascinating idea. It was revisited multiple times over the years. Some of the experiments that we are going to use is just realizing this interferometer in the solid-state device form. Already in the 80s, when people comes around the way that you can fabricate small-scale device, this is gold ring fabricated by the electron beam lithography in 80s technologies and IBM. The size of the ring is probably about 100 nanometer or those kind of scale. The first demonstration, close to first demonstration of nanotechnologies. And you can see that across this gold ring, cold enough temperature where the electron wave function is coherent enough in this side of this ring, under the magnetic field, the conductance across this gold ring start oscillating. And this oscillating period is surely related with the magnetic phase thread into the structures. And this is a good example of how one can use the Aron-Bohm type of effect, right? So in some sense, we just kind of make those kind of interferometer in the solid-state device that using that, and then that when the state is in quantum states. There has been some of these efforts in the quantum Hall communities already in the very early on 2003. You can see that now this is interferometer in the so-called Mach-Zehnder type of interferometer made into the multi-hyperlooms group at the Weizmann University, Weizmann Institute, whose group has been one of these real pioneer for this field for 25 years or more than 25 years, and close to first demonstration. This experiment is beautifully executed in the sense that they just demonstrated you can build up this the interferometer by just kind of installing the quantum point contact, which actually allows to partition the wave function in two different paths. So this is kind of electronic version of the beam splitter. And the path of this electron path that going through is basically determined by the edge state that you fabricate into the device. In this case, is etched edge states, etched device structures. But shape of this device and where the boundaries basically guide where the electron flow. And placing this quantum point contact in the relative place, the right places, you can see that how you can split the beams through. Measurement is relatively simple. You just measure the conductance across this device, right? And conductance is being measured by just measuring the current, and that's where the beam is combined, and then just give the full electron to the device. And current is basically related with intensity measurement in terms of the optical interferometer, right? So experiment is basically applying the magnetic field, changing the interference interferometer, the arm's length, which can be done by the gate, which can push around this electron path in and out, right? So you just kind of change the length scale and changing the magnetic field, which changes the amount of Bohm oscillation. They start to see that the red and blue stripes, which often is related the peak and the deep in constructive and destructive interference is kind of modulating, can be kind of demonstrated beautifully, and seeing that this interferometer actually worked. As just look at the phase changes into this electron wave functions, right? So this type of experiment has been going on in the past probably 20-some years ever since, and people have been pushing this into various limits and various structures here, somewhat different interferometer designed as our Fabry-Perot interferometer. Here the structure is basically electron beam is before it comes around, it's kind of winding around this cavity a couple of times, like the Fabry-Perot cavity, to pick up the information about the Bohm phases out of this type of the system. This was done by Charlie Marcos' group some years ago, up to this fractional cases. There has been some of the efforts in this community over the 20 years and try to demonstrate the existence of anyons. I would say that 20 years of effort was hard efforts. Part of the reason is the community discovered one by one of some technical challenge and have to overcome. I don't want to go over all the details, but probably about 4 or 5 years ago, there has been kind of really big breakthrough happens, and the very first example of the presence of the anyon start to shows up in about 5 years ago now, right? So this is the 2 experiments I'm going to show you here that happens about the same time in the 2020. And the first example is done by Michael Manfra's group at Purdue. Is the following experiments. So they use this interferometer. It's a Fabry-Perot interferometer. I just showed you previously. The same things, very similar structures. This is a quantum point contact, QPC, that in short we call, right? Partition the electron wave function, or in this case, anyon wave function. They put everything is 1/3 of the fractions, but they partition it and just kind of measure what is the anyon currents coming out the other side, and just kind of measure the interference pattern as a function of magnetic field and the magnetic field and gate voltage, which tune the area. In other words, basically tune this Bohm the oscillation, right? But what you see here is that the interference pattern is basically breaking the kind of few point. And in this few point here is related with that if this cavity is accidentally occupied by some number of the anyons there, each anyon jumped in, basically that will just break this nice kind of the interference pattern and shifted this patterns a little bit. And this shift is related with basically about 1/3 of the phase shift, which is 120 degrees, right? And if you just remember that if the anyons is getting there, the anyon is kind of braided, there's a kind of phase shift expected, and this break is in fact related with this phase shift coming from the anyon jump in, and that's kind of really interesting evidence one can present. Indeed, you can start to see that this anyon braiding statistics, right? About the same time, that group led by the Gendar-Fab at the ENS of France actually shows somewhat different experiments, but very similar conclusion. In this experiment, they just use one the quantum point contact, and they send this to 2 anyon through this quantum point contact. And then when anyon comes into the quantum point contact, they scatter off out of the quantum point contact, and they can measure it, right? And this experiment, in some sense, in quantum optics, are very similar to the so-called Hongwu-Mandel type of the experiment. In a sense, when that the either fermion or boson comes in, either they tend to bunch or anti-bunch through the beam splitter. In similar way, that when two anyon comes into this beam splitter, and then when they scatter off, due to this exchanges, the statistic, they may get kind of slightly different result. And just kind of looking at this, what is a cross correlation between the scattered light and incoming, one can extract information about the braiding angle. And out of this, the kind of beautiful experiment, they also show that braiding angle, exchange angle is very close to the 120 degree pi over the 3. And these two experiments, in fact, demonstrate kind of rather beautifully that at least that 1/3 of the fractional quantum Hall state, which is kind of the strongest, each quasiparticle indeed kind of exhibit this kind of braiding statistics. So that is kind of good, kind of beginning of the state. Of course, once this result comes around, and then correct that one of the important part is controlling this is a Coulomb interaction, which is delicate control that one can make. One can copy this experiment beyond this the gallium arsenide type of the platform where the other two experiments was done. So I've been working on this 2D material for a long time, and then now that quality of the 2D material, especially when you use graphene, the encapsulated boron nitride, and using this graphite top and bottom gates, as Leo Lee here in the brown demonstrated as well, one can get extremely high quality of the electron gas. And this high quality of electron gas, that one can envision that maybe one can use this for also quantum interferometry. Because in the bilayer graphene especially, it's not only that you get high enough the mobility, once you get in bilayer graphene, Leo also beautifully demonstrated that the even denominator state actually readily appears in this bilayer graphene with much larger energy scale. So in some sense, this can be an extremely interesting platform that to realize the quantum interferometry and push the idea of the creating anyons and manipulating anyon, especially non-abelian anyons, into the system. So it is very exciting. Maybe one can just apply the very similar idea that happened into the gallium arsenide into the system. So that's how that we start kind of get involved in here in a few years ago. And quickly we start kind of demonstrated, indeed, what has been done in gallium arsenide can be reproduced in graphene. One difficult part of the graphene is, unlike the gallium arsenide, we don't have the large semiconductor band gap. So once you just kind of try to deplete the particles and make the quantum point contact, you need a slightly kind of different technique. And here in graphene, although we don't have the gap, once you apply the magnetic field, that you can create this the Landau level, and that especially along this charge neutrality, there is kind of relatively large gap sets up, so-called nu equal 0, the Landau level separation. One can use that as a kind of depletion ranges. One can set up the more like the gap-like the structures, which means that unlike the gallium arsenide, we have to kind of put this all everywhere that the gates, and each of the segments, you can just segmentize this top gate, and each of the gate will define where my sample boundary and sample edges should look like. And in the end of the day, we can just set up something like this. Here is a gate, everywhere is a gate, segmented. But the important part is this is my QPC, quantum point contact, right? And here, this is the fabric pedal device. There's another QPC there. Right? These are two QPC that we can control that the QPC separation by just controlling the gate on the top. And there's 3 different gates which also set the different density that we just put that everywhere. For example, nu equal 3. There's 3 edge states kind of running around across this the quantum point contact. We can partition this particular edge state. At the end of the day, we just measure the transport across this device. And as a function of the gate voltage or magnetic field, you will see that this nice oscillation of the conductance that you're measuring through, and that's basically where the electrons start kind of create those kind of fabric pedals, the constructive and destructive interference. We can simply measure these things. So, okay. So this is nothing new. Has been done in gallium arsenide, but now we can just repeat this one in graphene with kind of all the gate controlled device structures. So at least that's kind of nice, right? right? Now, what we just kind of show you is Aron Bohm oscillation, right? Aron Bohm oscillation in a sense that if you just have this plunger gate when we control, that you can just change this area of this the fabric cavities a little bit, and this area got modulated by the gate voltages, and the transmission probability of this one is a 2qpc transmission coefficient, and and the Aron Bohm kind of oscillation period comes in. Most of the data we are getting is basically measured conductance as a function of the magnetic field, and the gate voltage we control the area. This is kind of what we are getting in the full scale. But of course, in the reality, we just kind of sweep the small area on the top here or somewhere there in the small range of B and gate voltages. Usually you will see that the pattern that I'm going to present of the data is kind of some of the alternating stripes of the maximum and minimum of the conductance as a function of the gate voltage and magnetic field. Often that we call this is a kind of what plasma plot, right? Note that here that all the phase is kind of really, really well defined, and there's no jump because this I'm just kind of showing the just electron or the non-anionic, the quasiparticle Aron Bohm oscillation, and that's why there's no jumps around here, right? So experiment that we can just do that is once you just do this type of the experiments, kind of apply this into the fractional cases. This experiment we just although try to do in the first generation and integer, we get extremely nice data. Once we push into the fraction, somehow we couldn't make it work. So certainly there is kind of further development is needed for the graphene type of the interferometer. So what we did is we made kind of slight device changes and improvement, and that actually worked in following way. So in this, the first generation device, basically we have the controlling the QPC, which is a very important range. This can be done by the global backgate, where both of the QPC is controlled simultaneously. But one thing that we just kind of did in the second generation device is a little bit more complicated, almost close to the first generation device, except that we have the additional gate that basically now suspended overhang across this sensitive QPC regime. And this overhang gate, which actually is a kind of technological development we made, breakthrough we made, I would say, allows us that we can control this the QPC, the transmission, without changing any other parameter in the device, magnetic field and all other gate voltages. So we can kind of gently tune this QPC transmission, and that allows us kind of the new type of breakthrough of the experiment, so we can just to do that, right? Furthermore, I think we improve this the quality of the QPC by improving this, removing the disorders in the system further. So with this, I think we thought kind of we are now really in the right positions to do the kind of exciting experiments. So the first thing we noticed that is already in integer quantum or interferometer, we get kind of fairly different result to what compared with the previous one. For example, that even for the integer quantum Hall, that we get this nice the Aron Bohm oscillation I just mentioned. If you have this two edge state kind of going through, and especially if you just partition the outer edges and leaving the inner edges is just isolated, you can see that oscillation start kind of shows up some of this breaking point, right? So that's kind of the phase breaking point I just mentioned there. And this phase breaking or phase jump is associated with, in fact, that charging events appears inside of this the edge state, and just kind of those kind of the jump is exactly related with capacitance coupling between this inner and outer edges, and that's kind of the one thing that we start to see. So seeing this type of result, we had a really, really high hope that applying this device to the fractional quantum Hall, we should be able to get this information about the Anyon braiding angle. So this experiment was now the same device I just showed you, simply just kind of bring it to the fractional quantum Hall state, something like the 1/3 or 4/3, which is one of the strongest the gap opens up, and ask that what type of the experiment we can get out of this, right? To briefly give you the sense that what we expect to see is the following, right? So again, we're just kind of using plunger gate to change the area changes, right? And I said that there are two information we expect to see. The one is the Aron-Bohm oscillation, and that oscillation period is related with the charges in there, right? So the other information is basically this exchange statistics, especially if I'm sending the anyons around, and if there's those localized anyons start kind of populating there, there is an anyon braiding statistics. Both of them will just contribute into the phase shift, right? So Aron-Bohm phases that this the plasma plot, the slope, contains about the fractional charge information, and those kind of phase jump that has been seen in gallium arsenide will just kind of give you that information of fractional statistics, right? So before we just kind of move forward, at least we should kind of reproduce what has been seen in gallium arsenide, right? So we just kind of, that high quality device we fabricated, we thought kind of, well, now we are getting to see at least what has been seen in gallium arsenide. The result was very disappointing in the beginning. So when Tom first, who made this device and measured this device at the fractional quantum limits, and he came with a pretty much kind of disappointment. And the reason is, well, to get this the interference signal, that we need our interferometer is absolutely stable, which means that if I fix all the parameters in my device, including gate voltage and magnetic field, and there should be no change in the signal. But with that condition, you still see that there's a kind of jumping around this conductance, right? Few percent of the jumping around the conductance, and this is already kind of enough to kill that all the signals that we expect to see, right? And you see that this signal is rather sharply jumping around. Often that this is what you call the telegraph noise, and often the cause of this telegraph noise, there is some sort of switches somewhere in your device. It's basically ruined your kind of the signals around. So we thought, you know, that yeah, you have all this telegraph noise. It's a probably useless device. Maybe we have to make the new device again. But then Tom noticed that following things. But look at this. I think that it's a telegraph noise, but it was somewhat different. It was rather than 2 level, there's 3 levels. You can see one signal is there, another level is another level. So if you make the histogram, in fact, you can make this nice 3-level type of histogram. And then Tom speculated maybe this is Y3 rather than 2 or 4. Because we are measuring the fraction of the 1/3 or the 4/3, where that 1/3 of the fractional charge do exist. And if you just think about this is a 1/3 exciton, the anyons, and then we expect to see that the phase, each of the excitons comes in and they give you this jump. And then after 3, then you will go back to the kind of the mode of the 3 to 1, kind of 1 again, right? Say 120 degree, 240, and then going back to the game, right? 0, right? So maybe this is kind of what we suppose to see. Well, that is kind of the bold the speculation, but out of this noisy signal claim that I'm seeing that 3 branches of the anyon is too much, right? So I just say, hey. That sounds kind of plausible, but I cannot buy that. But then there's kind of part. This one is taken that with everything's fixed. So Tom said, what if I just change something, right? What if I just change the plunger gate, for example? And indeed, that's kind of experiment he did. That now with this, the histogram you take, that the next you change the plunger gate a little bit, and just to take the another histograms of this one to record this 3 position, and that's kind of what he did. Right, plunger gate changes, and then immediately data shows up quite exciting result, right? So although we thought it was each of them is basically this random telegraph noise, but if you just kind of look at where those kind of 3 levels are changing with the plunger gate, they do changes, and sinusoidally, and each of them make the sinusoidal curve, and you can see that each of the curve is 120 degrees apart, and just immediately shows that indeed this is the what is coming from basically anyon numbers got changes, and we are seeing that the phase shift has a mode of the 3 of 120 degrees of the shift, right? So that was kind of really exciting moment that indeed this noisy signal start to give the really interesting statistics behind of that, right? In fact, that is what theory has been proposed for many years, right? And theory proposed that if there's a dynamics of this anyons, the occupation numbers, there that interference pattern will go through, that phase shift between the different branches, and if those kind of the occupation is suddenly happened, of course there's kind of sharp phase jumps happens, and kind of what we can see. So in some sense, seeing these three branches out of this the random telegraph noise, I think prove that indeed we have this Anyon braiding angles of the 120 degree, we can detect it, right? How about the fractionalized charges? And that we can just, we need to look at the Aron-Bohm oscillation, something like this. If it is an integer, I mentioned that those kind of slope in terms of the magnetic field with the gate voltage, which actually converted into the area, will give you about the slopes, the charges that carry this interferometer. But to get this type of the nice pajama plot, if I just don't change the magnetic field, basically I need the absolute the stability of my oscillation, right? But unfortunately, that what we have here is that even without changing magnetic field, there's a lot of the phase jiggling events happen. So there's no easy way that we can just construct those kind of pajama plot, right? Because each of this time sequence is related with the random phase shift. But there's a way that we can just reconstruct those pajama plot in the following way. Because of the this, if you just take the histogram, as I mentioned, there's three branches appears, right? And remember, that's kind of where I have the fixed magnetic field. What if I just kind of make these histograms with now the magnetic field is slowly changing? And you see that as we change the magnetic field, those kind of these three branches also do start to shift in terms of phase. And simply just looking at those kind of the slope onto this phase, the histograms, I can extract information about, again, the slope, that which actually tells you about the fractional charges, and no wonder that is 3 times larger than what we get in the slope, which means that charge is 3 times smaller than electric, the fundamental charge of the integer electrons, and in this type of things. So in some sense, we just kind of show that indeed we can just demonstrate both the fractional charge of the anyons as well as the braiding angle. So after we just kind of did go through this one, we just wrote down our preprint and put into archive and submit the papers. But that few days after, 2 or 3 days after that we submit the archive, I got a letter from Shankar. And then also separately, I got a letter from the Dick Reed. But as soon as I got the letter from the email from the Shankar, I just, even without reading, I know that I made some mistake in my preprint. Okay. So, and Shankar kindly explained to us that the mistake that we made is following. Shankar and both the Nick. Is basically, well, you know, that in this interference experiment, so what we are measuring is not the kind of exchanges, but it was double exchanges. In a sense, the exchange is changing the particle position like this, right? But the interference, we need kind of full way of this kind of rotation like this, right? So exchanges or this interference that what we are measuring, braiding, is basically double exchanges. You have to exchange it twice, right? Okay, good. So then instead of we measure exchange angle, we measure braiding angle. But there's another point Shankar made. You cannot use it even the braid, because braid operation is what mathematicians already defined in 1920s in this paper somewhere, right? Right? And that paper claimed that braiding is basically mathematicians call same as the exchanges, right? All right, fine. Then we can just call the double braiding, double exchange. It doesn't matter. It was a name. However, there's more things than nomenclatures. Because of these double exchanges, in fact, all the exchange, the interference experiment, including ours as well as gallium arsenide previously done, cannot measure exchange statistics unambiguously. In other words, basically we can always access only the 2 times of exchange angles, which means that there's always a sign ambiguity in the system. In other words, if I just do this experiment with the electron, I cannot distinguish whether it's electron versus bosons, right? Because it's twice, basically, I just kind of lose the sign information, right? Same thing, right? So fine, okay, so that's kind of a more serious problem. But interesting enough, then around a similar time, there's some other theoretical proposals comes around. In fact, one can just distinguish this one in principle. And this is basically the theoretical proposal done by Steve Kiverson and Chaitanya Murthy with kind of following idea. So imagine that I have the Fabry-Pera the interferometer, but there that if you just put the quantum dots in here, or more precisely quantum antidots, and whole purpose of this the antidot is basically you can populate the anyons or depopulate the anyons into this dot, right? Imagine that there is no anyons into this antidot. And then when we just construct the interference that it comes around and just kind of tunnel through this QPC and comes back and we measure it. But because it's empty, well, we can just go through this antidot and just comes around. And you don't see that if this antidot is empty with anyon, don't see that typical kind of differences in terms of this the interference patterns of the phases. However, if this antidot is occupied by the anyon, there's a particular process is possible. First, the occupied anyons comes out from a dot and just kind of going through, and the other anyons is now occupied the unoccupied antidot, and while this anyon comes around, come back to the original position, used to be the other anyons is in there. And if you compare that, that's precisely the situation. These two anyons just change the positions, right? So this cooperative tunneling process, if you just do measure, will actually shift that the phase of this interference exactly of the exchange angle. So instead of 240 degrees of the phase shift, you expect now 120 degrees, right? Do we actually can get this type of things? Experimentally realizing this type of the situation, device situation is extremely tough. Part of the reason is, well, already our QPC is about 100 nanometer size, and building up another quantum dot in there is a very, very difficult task. However, again, the nature actually helps us a little bit in this side. Although we cannot control the precisely, there are enough the disorder can make the kind of small puddles around, and especially near the QPC region, that one can make this kind of puddles close enough to the QPC, work like this antidot we want to create it. And more importantly, we have the gate near this QPC that control precisely the QPC region. Using this gate, in principle, we can just kind of occupy and unoccupy this dot into the situation. How do I know? If I just measure simply that this QPC transmission by just measuring the conductance across this one of the QPC, changing the QPC gate, you start to see that conductance is supposedly that 1/3 of this one, but then there is some of the oscillation, very sharp oscillation, and this is first going to the dip, but it gets into the peak. And in fact, if you just zoom in one of this area, especially this type of the sharp resonance part, and changing the source drain bias voltages, you can see that source drain bias voltage versus gate voltage, there is a conductance, the resonance appears, and that's kind of this the nice diamond shapes appears into as a function of the bias voltage and gate voltage. Anyon work on the quantum dot transport, and this is very similar to the so-called stability diagram that you expect to see the quantum dots. And that's kind of what we are seeing. So according to that idea, each of the time that as a function of the gate voltages got changes, we expect to see that anyon occupation number onto the quantum dot should be changing. If this is even and the other side is odd, or if this is odd of this anyons occupied, that the other side, not even. If the anyon number got changes and there is a kind of level number changes expected into this system. So experimentally what we need to do is basically comparing the interference across one of this resonance. Indeed, that's kind of what we did. If I just compare, this doesn't go, the interference of this, across the occupation number, you can see that the interference of this three-branched interference exactly shift about 120 degree of the phase shift. Sorry, 60 degree of the phase shift, indicating that we can pick up this the anyon braiding exchange informations out of this type of the experiments. Again, this shows that we can now go even beyond of what has been done in gallium arsenide. We start to see that not only double exchange braiding angle, that exchange braiding angle immediately out of this type of the techniques. Right. So that's kind of already showing that we are catching up that what has been done in gallium arsenide using graphene as a kind of platform. In some sense, we have the, a little bit of this, the more flexibility to fabricating devices, including all sort of different gate configuration of the gallium arsenide. We are getting into the a little bit better statistics or better proof of has been done in gallium arsenide. So I think that is a good kind of starting point. Where we are going? The next step is, of course, can you actually control the this random occupation a little bit more deterministic way? Can I just control the number of these anyons into this dot better? Already you start to see that this accidental dot we fabricated or we utilize shows that those kind of process. Instead of this accidentally formed dot, one can even possibly that create another gate structures and just kind of control those occupation. And furthermore, that we can push this into the even denominator states. Right now, the experiment I showed you is a single layer graphene, which does not the host is even denominator state. But bilayer graphene, you can get this the even denominator state with a rather strong energy scale. And in fact, not surprisingly, Yuval Ronen's group that in the Weizmann University I mentioned before, this is a very recent experiment. They basically using very similar device structures, now getting that similar out-of-bomb oscillations start to appear even in even denominator states. So progress in the field becomes really accelerating now. I think already in gallium arsenide, graphene, abelian the Anyon states can be shown and manipulated can be done and various things. Now the field is really quickly moving even denominator states. So hopefully that we can start to get the glimpse of this the braiding of the non-abelian Anyon very soon. All right, so I think that I have only 2 minutes, 1 minute. Yeah. So I just kind of prepared another part, but this part, unfortunately, I have to probably rush it through that. I don't want to dwell too long, but at least give you a little bit of flavor that what is the other platform that I mentioned, right? Other platform that I mentioned is the combining topological materials with the superconductor and create the topological superconductivities, right? So example I'm going to share is kind of some similar phases here, but it's mostly done by the Junyoung Park, who is now returned back to the Korea. Here's Yuval Ronen again, Ami Yakovitz, and different set of the theorists. But here the sample is coming from the Princeton, the topological insulator, the best quality topological insulator with the intrinsic coming from Bob Carver's group, and that make this experiment to work it out. I'm going to tell you a little bit of this Anyon that called the Majorana here. One important difference here is again that quantization of magnetic flux is important, but note that previously quantized magnetic flux is h over E, because now we are dealing with the superconductor that becomes h over 2E. But otherwise that the notation is kind of similar. Idea is again somewhat old, and it's almost dating back to what Fu and Kane's original proposals. So in 2008, this very seminal work of the Fu and Kane showed that if you just kind of proximatize a topological insulator surface with a superconductor, you can get this the Majorana mode in there. And in fact, if you just kind of make the rather than Josephson junctions with the channel, but this two channels meet into this tri-junction limits by just biasing this multiple superconductor with the different phases, you can create this the Josephson vortex at the position, and this Josephson vortex contains isolated Majorana there. And if you're clever in this paper, again, they went on that if you combine these two tri-junctions, and there is a way that you can control the phase of the superconductor that create and that even just braiding this Majorana into this device form, the Josephson junctions made onto the surface of topological insulator. So this idea has been kind of pushed along, kind of the many cases. And the people indeed try to make this Josephson junctions on top of the topological insulator, 2D, 3D, and 2D. And sometimes you just have the semiconductor heterostructure with a strong spin-orbit coupling. With the in-plane magnetic field, you get very similar structures out of that. And there's a tantalizing, again, evidence that you can see that the evidence of the Majorana by the tunneling experiments, or that, say, missing the 4 pi, the second steps of the Shapiro step experiments, or the Fraunhofer patterns. There are some of the evidences are there, but most of them are rather indirect yet. Part of the reason is really true evidence should comes in that demonstrating, can I just kind of really braiding this the 2 Majorana and see that your fermion parity changes. So that is kind of tall order, and some of this progress has been made that there is no really smoking gun yet. One can claim that I'm seeing the braiding statistics. And one of the part, a really difficult part of this the experiments is also coming from the quality of the materials, and indeed, including the very recent Microsoft demonstration of this kind of braiding experiment of the Majorana. Basically, it is struggling that how you can just kind of fight with the disorder, and that is kind of one of the biggest problems there. And of course, the field are making some progress, and here's one thing. Here's a good example. Bob Kaba's group make the 3D topological insulator, and they have the really kind of careful control of this compositions as a doping. Finally, they could make the at least topological insulator becomes really insulating, which means if you get into the bulk, the chemical potential is well within the bulk, and there is no bulk conduction. The carrier density in the bulk is less than 10 to the 15 carrier per the cubic centimeter, which is basically almost electrical grade of the insulator, you can see. And that conduction is only through the surface state, and that's kind of something that demonstrated. Even for this type of sample, however, once you just put the superconductors on the top and try to do the fabrication, surface where you need to kind of do the proximatizing start degrading. So how to keep the surface and keep the device quality during the fabrication is a rather difficult part. And there that over the time that many people, including us, that developed a way that you can passivate the surface with the tellurium or other materials and only do the fabrications with this passivated layer and remove this passivated layer before the depositions and protect the surface. And there are all kinds of experimental details there, but in the end of the day, that you know that how to make the really high quality Josephson junctions out of this topological the surfaces there. And the other one is basically what type of the device you want to fabricate it and demonstrate that indeed you can just kind of create this Majorana and demonstrate this kind of braiding type of defect. And one nice device geometry is, for example, the Kobino device geometry, which means that now there's a contact, inside contact and outside contact, and this is from the Josephson junction. And then you can apply the magnetic field in this device. And magnetic field will penetrate this non-superconducting region, which means that nicely sit in this junction region. As I mentioned, this magnetic field that penetrating with the vortex and center of the vortex in the normal state, where the Majorana sits in there, right? So anytime that you control the number of the vortex, which is integer number, you can control the number of the Majorana into the system, right? Even nicer, now if you apply the current through this Josephson junction, supercurrent will start to move around this the vortices. That is basically Magnus effect, right? So sending the current, vortex start kind of spin, the rotating around, right? That's a natural way that I can just do the braiding, right? How you can read it off? Well, then you can just kind of get the idea from the Fu and Kane's original idea. If you start kind of segment this, the superconductors and create these tri-junctions, there's a way that you can trap your vortices there or that in there. So for example, if you make those kind of the Kobino device, by the way, this is a real device structures. This segmented in this way. I think I'm not in the generation, but my postdoc Junyoung called this a pokeball. I don't know why. And that's the structures. You can create the vortices and just kind of move things around, and you can manipulate it by just phase biasing. So I don't want to go through all the experimental result there, but let me just kind of pass through there and just kind of give you one punchline. And indeed, at least this type of the device, work it out. we don't yet get the Pokemon style of things, at least the Covino device, Pokeball style. And what you see here is basically we are measuring the critical current onto this Covino device I just mentioned. The central part is need to be contacted by these air bridges. So this is current is oscillating as you change the magnetic field, and this oscillation is related with number of the vortex I just drawing there, right? But what you notice that is this current is basically not symmetric. And in other words, there's a Josephson diode effect, which is not surprising, by the way. But if you look at this, how the diode polarity changes, the polarity changes positive and negative numbers, and they're basically oscillating as we change the number of the vortex. But you can quickly see that this period of the oscillation, of the modulation, is not just every vortex gets in there. In other words, even number of the vortex, odd number of vortex will give you a different polarity of this oscillation, which is basically another way to saying the 4 pi, the periodicity. That what is it? One of this very important evidence of the presence of the Majorana. And one time actually go through all the details, and it is related with, in fact, the number of the Majorana we can control in this device in discrete way, and the Josephson diode effect is a nice way we can pick up this the parity change in there, which is kind of rather important the first step, so showing that this is really kind of worth working out. All right, so all of these things I mentioned, in a sense, is just kind of progress report, right? So let me just kind of skip all these things. But nevertheless, I think both on this quantum platform as well as its topological superconducting platform, I think that the communities are now making really meaningful progress, going beyond that just existence proof, but showing that how we can manipulate them. And what is the next steps that we just kind of go through, the demonstrating this braiding and operations, and just kind of result of braiding. So my expectation is kind of within next kind of few years of time frame, I think both of this community will kind of make the more meaningful progress. Not sure whether quantum computing is really possible out of this type of system, but at least kind of really solid steps to showing that braiding is possible, and that braiding outcome we can just read. So that's kind of the expectation. Thank you very much for your attention.
Okay, thank you everyone for staying a bit longer. Let's have maybe 1 or 2 questions, then formally close. And everyone has a question can come down and ask Philip Kim right here. Do we have a question? Okay.
Great talk, Philip. Congratulations on all this great work. On the accidental pothole that you created there under that bridge, if you warm the device up next day when you perform the same measurement again,
Yeah.
Is the pothole still there?
Its puddle is still there. I think the details a little bit changes, but the existence puddle is there. And then, although I mentioned it's accidental, it was not completely accidental because